Okay, so this is a fun problem that sheds a very lot of light, I think, on how exponential objects work and how we can understand about sort of how they relate with this Mitchell-Benerbau language. So we're going to consider a problem. The problem is as follows. We have a point x given to us of object A, and we have a point y of object B. And what we want to do is get all of the arrows which send x to y. So we're looking for all of the arrows f, such that f of x equals y. Now, look at this extension. So our free variable is an f, and we want to do fx equals y. But notice that this f is actually part of an exponential object. So what we really want here is the kind of subobject of the exponential object, which represents the kind of stuff that sends x to y when we evaluate it. So notice here we're using round brackets, and of course we've got a hat on our f because it's really living in the kind of exponential space. It's sort of been transposed. And so this round bracket stuff is actually just shorthand. And what we really should write is this. So we're interested in the extension of the type omega term E f transpose comma y, E f transpose comma x equals y. Okay, we want to find all the f transpose, all the f bars that make this work. We want to find the subobject of them. Okay, so we're going to do this, and it's a very interesting kind of problem, and we'll see that we get a result which makes a lot of sense. So let's just go ahead. It actually doesn't take much writing. So we have a point x of A, a point y of B. These are given. And then we're interested in this extension here, which is the subobject classified by the interpretation of E f bar comma x equals y, where the variable is f bar. So the question really is what's the interpretation of this? And that's the trickiest part, I suppose. Well, we want to interpret E f bar comma x equals y. So when we interpret, firstly, we want to change this equals thing into a delta thing. The y is a constant, so that becomes y exclamation mark b to the a, because our only free variable is in b to the power of a, this f bar here. Then interpreting, we can shift past the e. Interpreting the f bar, it becomes an identity, 1 b to the power of a. And interpreting this x, it's constant, so it becomes x exclamation mark b to the power of a. So this is the interpretation, and what we're interested in then is when doing this interpretation on v bar equals t, that's the condition for v bar to be in this extension, where v bar, we're assuming, is just an arrow from the terminal object to b to the power of a. So what we're really doing is investigating when v bar is going to be a point of this exponential, of this subobject of b to the power of a that we're trying to find. So, I mean, this diagram's pretty illuminating. So this big green arrow, this is the interpretation thing that we're after. And this is just the pair. Well, this is just actually this purple arrow before this delta arrow. Well, this delta arrow is the classifying arrow of the diagonal here. And this purple arrow is the pair of y after exclamation mark b to the a, and e after 1 b to the power of a exclamation mark b to the power of a. So we're interested in when v's in this orange arrow, this extension here, this subobject, but that's happening precisely when doing this green arrow after v gives us a true. Okay. So we have v is in this extension if and only if v after this arrow gives true. Now what we can do is, sorry, v bar I should say, not v. And what we can do is take this v bar inside the bracket. So when we take it inside here, this y exclamation mark b to the power of a v bar is just y, because we then get exclamation mark from 1, which is just gives us a y. Similarly, taking the v bar inside and hit this thing on the left, into here gives an x, into here gives a v bar. So we're left with this simpler expression that delta b after e v bar comma x comma y is true. That happens if and only if this stuff inside the brackets is in the diagonal, which happens when the left thing in the bracket equals the right thing in the bracket. So our critical condition then is that e v bar comma x equals y. And that's very cool because that happens if and only if v, not v transpose, but v after 1 comma x equals y. And we can see that by looking at here. So we can see this because this v bar times 1 thing is actually v bar p1 comma p2 paired. And so doing this after this picks up the 1, which doesn't change anything, and this p2 picks up the x. So these two composed are v bar comma x. So we see that e after v bar comma x is equal to e after v times 1 after 1 comma x is equal to v after 1 comma x. Hence, this is true if and only if v after 1 comma x equals y. And that's very, very cool because that's just what we wanted, really. I mean, the thing is, when we pitched a question like this, of course, the transpose of this point v bar of b to the power of a will indeed be an arrow v from 1 times a to b. So, but we can see that it's the correct one. It's the one which if we input it, if we give it an input which is just like something null in the terminal object, together with x, we get in A, we get y in B, which is precisely what we want. We can actually go a little bit further. We can define v underlined to be v after exclamation mark a comma 1a, and then we can rewrite this as v underlined p2 1 comma x, which is just v underlined x. So basically in this case we have that v transpose is just the name of v underlined. So in other words, this kind of expression in orange here just gives us the subobjects that's points are the names of the arrows from A to B that send X to Y. It's really very simple. But it all just works out so nicely. So yeah, there we are.